Hi, everyone. What I'd like to walk through today is just a full review, it should all be a review topic, of us dealing with powers. So you'll see the title up in the top left. We're going to address some powers. The goal for today is to go back and just kind of refresh a little bit everything that goes into working with powers. Today's lesson, in terms of a recorded lesson, is going to run a little bit different. What I want you to do is I want you to pause the video on every slide. And so I'm going to tell you when I want you to pause it. But what I want you to do is I want you to answer every single problem on the slide. Because each one of these instructions, these problems, are all going to deal with a different thing. So let's kind of train our gut a little bit. Let's see where our gut leads us. But let's try to tackle every problem within each section. So you see on this one that we need to state the expression in power form. And so whether you have a lot of confidence in the problem or very little confidence, what I'd like you to do is to pause the video when I say and tackle every single one of these problems. Okay? Pause it now and give it a shot. Okay, so we're back. So when it says power form, then that means that I need to express everything as a power. And to write something as a power means that it has two components, a base and an exponent. So if we take a look at the solution to the first one, to follow that instruction, I have 4 to an exponent of 3. 4 is my repeated multiplication, and it shows up 3 times. You take a look at B. B would then be a negative 3 squared. Since we don't see any operation, we know that there's multiply. In question C, we would also have a 1/5 squared. Just be very, very careful that we did not write this. The green means something very different than the blue. Notice the blue has as its base 1/5. The green actually has as its base 1. To write it very clearly, what the green actually represents is 1 squared divided by 5. And we can see up from the original form that what's being repeated in multiplication is 1/5. So we need to make sure that we have those brackets around. You then take a look at D. M shows up a repeated number of times. How many times? Exponent 5. So there's m to the 5th. So all of those blues represent your power form. Hopefully things went well. Let's take a look at the next problem. Now you take a look at problem 2. State the base and the exponent of each. So let's take a look at the 3 problems that you have. And all you need to do is draw an arrow if you want to identify that this is the base. We can label those as B, and this is the exponent. We can label that as E. So I'd like you to give all 3 of these a shot. Pause the video now. Okay, so we're back. So you take a look at the first one, and what we have then is our base of 4 and our exponent of 3. Okay, let's take a look at B. B shows up a base of negative 5, and I can see that that was put to an exponent of 2. Okay, now when you take a look at C, I'm going to bet and say most of us have C incorrect. I'm actually going to write these down at the bottom, just so that there's no confusion. I think for everyone that we could write the base equals, the exponent equals, and our exponent being equal to 3, everyone should have got. However, there's going to be a real common mistake here. In the expression in problem C, our base is 8. The common mistake would have been to list negative 8. But we have to be very careful at the difference between question B and question C. Notice that in B, we put down our negative 5 squared. And you can see that the base is negative because it's put in brackets. But then when you take a look at C, we don't have any brackets around that negative 8. So what does problem C's expression really mean? It really means this. I have a negative 1. That's what that negative out in front of that 8 means. Times 8 cubed. And so since if we relate back to BEDMAS, to our order of operations, we always have to do exponent before we do multiply. And so when I examine my negative 8 cubed, for me to follow order of operations means I would have to calculate my 8 cubed. My negative is not part of the base. So let's watch out for that one, because that's going to be a common mistake as we move forward. Okay, hopefully that went well. And if we didn't get C and we now understand it, then I think we're doing great. Let's keep it going. Okay, take a look at the instructions on the screen now. We have to write an expanded form. So you're going to tackle all 4 of these problems, writing each in expanded form. So let's give them all a shot. Pause the video now. Okay, and so we're back. So when we take a look at A, if I had to write that in expanded form, then that just tells me that I'm going to write negative 1.3 times negative 1.3. And it doesn't matter how you want to write it. So we could have written it in the blue form and said negative 1.3 times negative 1.3, except we do encounter a problem with a double sign. And you can see your double sign right here. So to write that in good form then, we only have to put brackets around the second one. Either of those forms are great. Okay, we take a look at problem B. Now I have 2/3 all cubed. Well, then that's going to be a 2/3 times a 2/3 times a 2/3. Now we take a look at problem C. We have our negative 4 squared, and we're not going to fall into that trap. We probably recognize, and hopefully, given the last slide, that negative is not a part of the base because it's not inside brackets. And so my exponent of 2 only applies to the 4 and not to the negative. So how do I now write that in expanded form? We would write that as a negative 4 times 4. Now, you can write it that way, and that's totally fine. That is the best form. But you could also include that as a negative 1 times 4 times 4. I'd accept either of those. Both show your understanding that the base is a positive value. Okay, now we take a look at D, and my guess is D would be pretty straightforward, even though we have yikes, that's getting a little messy, guys. Now, I do want to get to a little bit how we think about exponents. And so when we write something in expanded form, we just have to be very careful. So down below, I'm just going to put down a very basic a squared. And I just want us to think about our wording when we have to describe a squared. So what does a squared mean? And quite often we get taught when we're younger that a squared means that you're going to take a and multiply it by itself twice. I think we just have to be very careful with that. Because watch what happens if I take a and I multiply it by itself twice. There it is. A multiplied by itself twice. Now, we know that that's not what a squared means, but we have to be very careful on our wording. So, let's get rid of that then, and let's actually recognize what an exponent means. It means repeated multiplication, and so it tells us that we need to have two of the same base. So two of the bases. What was that base? It was A. So my answer is A and an A. And what an exponent means is repeated multiplication. So I need to have those two A's separated by multiply. That's what an exponent means. And so when we see something like, what is x cubed? Well, it tells you that you need to have three of your bases, all separated by multiply. And there we go. We're going to get challenged on that a little bit, especially as we progress. So let's make sure that we've got good wording when we talk about describing powers. Okay, let's keep it going. Now you take a look at problem 4. And problem 4 is going to ask you to do two things. First off, you'll see that we need to write each power in expanded form. Then we have to evaluate it. So if we're a little unsure about what the instruction to evaluate is, because we're fine with expanded form, we've already reviewed that today, then another word for evaluate would be calculate. So what this problem then says is, first write each power in expanded form, then calculate it, evaluate it. So you notice you have 4 problems on the screen. I want you to try all 4. So go ahead and pause it now. Okay, we're back. So my first action on problem A, 5 squared, would be to write it in expanded form. So that means, since I have an exponent 2, I have 2 of those 5s separated by multiply. Okay, second part now is calculate. So if we evaluate that, there's my 25 and we're good. Let's take a look at B. Now I have to write that in expanded form. So I have negative 2 cubed, which means I need 3 negative 2's all separated by multiply. Now I can calculate that. Well, I have a negative times a negative times a negative, so that's going to give me a negative answer. And then I've got 2 times 2 times 2, which gets me up to 8. Let's keep moving on to C. I need to write 3/4 cubed. So that tells me that I have 3 fractions of 3/4 all separated by multiply. Now I can go ahead and I can calculate it. And on top, I've got a 3 times a 3 times a 3. Well, 3 times 3 is 9, times 3 is 27. And on the bottom, I've got 4 times 4 times 4. So 4 times 4 is 16, times 4 is 64. We learned back when we dealt with squares in our review that there is a faster way to square a fraction. Well, there's a faster way to evaluate any fraction. If I didn't ask you in the original problem to write it in expanded form, and I simply said evaluate, maybe we can recall that I could apply that exponent to all parts of the base, so the top and the bottom of the fraction. And you can see that we could have gone straight to that blue answer. Since the problem said that we had to write it in expanded form, we had to include the red line. But if it didn't, you guys could evaluate by going straight to cube the top, cube the bottom. And there we have our 27 over 64. Okay, last problem D. I need to write it in expanded form. Well, that means that I'm going to have 4 zeros all separated by multiply. And hopefully pretty quickly, we know 0 times any number is 0. So if I have 0 times 0 times 0, then I still arrive at 0. Okay, hopefully those 4 problems check out. Let's move on to the next one. Okay, so let's take a look at problem 5. We have to write each of these numbers as a power of 10. So to answer that instruction, for problem A, you have to figure out, okay, well, what power of 10 is 100? Or for B, what power of 10 is 10,000? How could you write each of those numbers as a power base 10? So I want you to give all 4 a shot. Pause the video now. Okay, we're back. So hopefully we were good to be able to work our way through the first one and say, well, we know that 100 is just 10 squared because we know that that's 10 times 10. I'm hoping we actually know a trick to deal with all of these numbers as powers base 10. Now, maybe you work your way through and you take your time and you say, okay, well, 10 times 10 gets me 100. And then if I take 100 times 10, that gets me 1,000. And then if I take 1,000 times 10, that gets me up to 10,000. And so at the very least, we could work that out, that would be 10 to the exponent 4. But maybe even within the first 2 problems, you can actually see our trick, if you want to think of it as a trick. Notice that your exponent is the number of zeros. And so maybe pretty quickly then we could say, well, we know then that 1,000 is 10 cubed. And in D, where we have 10 million, you could have spent some time on D dealing with that blue way, but instead now we can just say, well, that's 10 to the exponent 7. Okay, real quick. That's something super useful, especially when you're sitting in a science class where we start to talk about scientific notation. Okay, let's jump into the last kind of type of big problem. What you'll notice in question 6 is that we now need to write each of these as a power of 2. So you have to be able to write 16, 64, 32, 128 all as powers base 2. So I want you to answer all 4 of those problems. Pause the video now. Okay, we're back. So we take a look, and maybe we just start building out our 2, and then if I double 2, I get to 4, and then if I double 4, I get up to 8, and then if I double 8, I get up to 16, and so on and so on. That maybe we can see from just that little series that I wrote down at the bottom, kind of that sequence of numbers, that we end up getting 2 to the exponent 4 for 16. I'm going to tell you guys that I think you are doing pretty well and that you have everything you need. If you can tell me your powers of 2 up to 2 to the 5th. So when we happen to see that that's our first power of 2, there's our 2 squared, there's our 2 cubed, there's our 2, yikes, to the 4th. If you knew one more power of 2 off the top of your head, I think you have whatever you need. Because then we can just kind of build from it. So what would be the next power of 2? Well, if we doubled it once again, that would be 32. And I'm just going to put in that would be 2 to the 5th. Well, I think if you know those 5 powers of 2 off by heart, then from your powers of 2, you put yourself in a really good position to be able to work with all of these ideas easily. So let's take a look at B. I've asked you for 64. But the largest power of 2 that you know is 32. Well, then you take that 32, and now we start to double it. And we're all probably pretty good at doubling. So to double 32 gets you up to 64. Well, that was your 2 to the 5th with an extra power of 2. And therefore, we end up getting our 2 to the 6th. So by knowing 2 to the 5th, we can start to build some of those higher powers of 2. For question C, we know that one cold. That is our 2 to the 5th. And now we take a look at D. So the highest power of 2 that you know, 2 to the 5th. Okay, so we double it to get up to 2 to the 6th. That's 64. And now we double 64, gets us up to 128. And that gets us our 2 to the 7th. If you know your powers of 2 up to 2 to the 5th, then I think you're good. Powers of 3, you'd really like to work to get up to 3 to the 4th. Powers of 4, we really like to know up to 4 cubed. Powers of 5, if you can get up to 5 cubed. And then any numbers that follow that, if we know our squareds, then I think you're pretty good. So invest some time today trying to practice some of those powers up to each of those I've listed. It's going to really pay off when we start to get into some other concepts. Okay, I'm going to throw kind of a bit of a weird one at you now. You guys take a look at problem 7. If you can read my messy cursive, problem 7 says, decide whether each statement is always true, sometimes true, or never true for positive values. And then you read problem A, and here's the statement, that twice a number is smaller than the number squared. Okay, twice a number is smaller than the number squared. And you have to try to decide, okay, is that statement always true, sometimes true, or never true? The only possible values that those numbers could be have to be positive. We're not including any negative numbers. Okay, what I want you to do is I want you to pause the video, give this one a shot. Okay, so there's a couple things to kind of discuss as we go through this problem. First off, you notice I've used some colors in the problem. To prove that something is always true or never true, kind of those two extremes, then you either have to show that something is true for all of those cases, or you try to come up with an instance where it's not. Sometimes true is kind of the one that fits in between, and therefore, well, sometimes true can be the most difficult one to answer. Because as soon as you think of one case, we might end up falling into that category. So I want to walk through this first one a little bit, just so we can kind of see some things and maybe some strategies to try to answer the question. Twice a number is smaller than the number squared. And so what I would recommend to you is, since the question says that this is true for positive values, then why don't we pick a positive value? Test it out. Test that statement and see what category it tends to fall into. So let's pick a nice easy number. And maybe I go through and I'm going to choose the number, 4. Oops, that really jumped on us. I'm also going to shrink that back down. There we go. So I'm going to choose the number 4. And so I'm just going to write sub 4. That's my number I've chosen. So that says twice a number is smaller than the number squared. Okay, so I'm going to try the first part. Twice a number means calculate 2 times that number. And I'm going to compare that to, so I'm just going to write like verses in there, a number squared. So 4 squared. So I calculate that. Well, 2 times 4 was 8 versus 4 squared, which is 16. So my statement said twice a number is smaller than the number squared. And right now, twice a number is smaller than the number squared. That would make that statement true. Now I have to decide, is it always true or sometimes true? We've ruled out the never true because we just found a case. So now I'm on the hunt to try to find a case where it doesn't work. If I can find a case where it doesn't work, then my answer is sometimes true. If I can't come up with an instance where I can disprove that statement, then I know I must be always true. So maybe we just pick another number and you check 5, you check whatever, you check 1,000,000, you check. Or maybe we can start to try to see, okay, when I double something, how does that relate to squaring something? So let's say that I went and I chose a really easy number, like 2. Well, twice a number means double it, versus squaring a number means multiplying by itself. And we'll notice that in both those cases, we get 4. Well, the statement says twice a number is smaller than the number squared, and we just came up with the case where it was not smaller. It's actually equal. We just disproved the statement. And so because we came up with a statement where it was true and then a statement where it wasn't, we can now say confidently that it is sometimes true. Just as another instance, before anybody starts to draw a conclusion for themselves, let's imagine that we sub in 1. If that was my number, okay, twice a number versus a number squared. Well, if I actually calculate that, 1 squared gives me 1. I actually have that twice a number is larger than. Like it's almost the opposite of the statement that was given. So there we can come up with a case where once it's true, and all I needed to do was come up with one instance where it wasn't, and therefore it was sometimes true. Okay, let's see if we can take that same setup but talk about a different argument. And so, as we take a look at problem 7, same setup, always true, sometimes true, or never true. But now our statement is the cube of a number is greater than the square of a number. Okay, the cube of a number is greater than the square of a number. So I'm going to say to you, pick a number again, and let's see if we can come up with something. So how about we pick like the easiest number to work with? I'm going to sub in a number of 1. Okay, that says the cube of a number is greater than the square of a number. And we notice pretty quickly that that statement is not true. If that number was 1, then they're equal. Okay, so right now we just found this case did not work. So now what we need to find is that statement never true or sometimes true. But at the very least, we've ruled out that it's always true. So let's pick another easy number to work with. Well, 2 is a nice easy number. And so I have 2 cubed versus 2 squared. And when we calculate our 2 cubed, there's our 2 times 2 times 2. And we calculate our 2 squared. There's a case where that was true. So we came up with a case where it was never, or it wasn't. We came up with a case where it was, and therefore it's sometimes true. Now, for interest's sake, I want you to notice that all we've been working with have been whole numbers because those are easier numbers to work with. I'm going to choose something a little bit different. We're going to choose 1/2. Notice 1/2 is a positive value. It's just a little bit of an uglier one. Or in this instance, I want you to think of it's a really small one. Because watch what happens when we now deal with 1/2 cubed versus 1/2 squared. Okay, well, 1/2 cubed is going to be 1 cubed, 2 cubed. 1/2 squared is going to be 1 squared, 2 squared. And you can actually see that the cube of a number is smaller than the square of a number. Play around with that a little bit in terms of your practice. And make sure that we're good, that because we are putting a cube, a higher exponent than a squared, on a number less than 1, we're actually going to produce a smaller and smaller value. Interesting feature of having a base that's less than 1. Okay, last one. You take a look. Same thing, always true, sometimes true, never true. The statement in this case, powers with the same base but different exponents are equal. Okay, I want you to pause the video now, give it a shot. Okay, we're back. So, maybe we have a case where we're going to try the easiest number to work with. We're going to try 1. Powers with the same base but different exponents are equal. Okay, so let's create that situation. Powers with the same base. I'm going to use a base of 1. But different exponents. So maybe I pick like an exponent of 2 versus an exponent of 3. Notice that gold statement represents the statement in the question. Powers with the same base but different exponents. Now my statement says that they're equal. Well, if I calculate each of these, I get 1 and I get 1. Those are equal. At the very least, I ruled out never true. Hopefully you picked another value to check against, and maybe you subbed in an x value of 2 or a value of 2. Okay, that means I have a base of 2 versus a base of 2, and maybe I just picked the same exponents. I'll try a squared and a cubed. Powers with the same base but different exponents. So if I calculate the first one, I got 4. If I calculate the second one, I got 8. Those are not equal. No. And so I found an instance where it was. I found an instance where it isn't. Therefore, it's only sometimes true. And there you go. So just us playing around with how do we test some statements? Can we test the validity of those statements? Okay, that should give us a pretty good powers review. Your job now, jump in and get some practice and make sure we're good to go for tomorrow. Okay, good luck.